In this video, we're going to talk about the first of 3 tests that we can perform on categorical variables. And this test is called a goodness of fit test. A goodness of fit test, commonly called a GOF test, is used for claims about a single categorical variable. So we should have one categorical variable, we should have one population, and we are comparing the observed frequencies from our population to the expected frequencies of the distribution, or the claimed values. And like all of the tests we're performing this week, we will be using the chi-square distribution to perform it. So to perform this test, we know that we follow the 4-step state plan do conclude. For the state, we're just defining the variable of interest, identifying our hypotheses, and sorting out what we're given in the problem. For problems like this, I need to make a table of the observed frequencies, so these are the ones from my sample, and then the expected frequencies, which are the predicted values. It is possible that we may need to calculate these. And in general, calculating these expected frequencies is going to fall into one of 2 categories. We will either be told that the values are split equally among all of the categories for our variable, in which case I'm just going to take the sample size and divide it evenly by the number of categories. The other possible option is I will be given a proportion for each of the categories, and I will need to take my sample size and multiply it by the proportion. So n times p for each category. Once I've filled in the table, I'm going to identify my test, in this case it's a goodness of fit test, and then check that all of my expected frequencies are 5 or larger. And this check is going to be true for all of the tests we're doing this week. Once I calculate my expected frequencies, I want to check that they are all 5 or bigger. If they're not, I should not be doing this test. The do stage looks the same as it does for all of our other hypothesis tests. I'm going to calculate a test statistic and a p-value, and I'm going to draw an appropriate labeled curve. We can do this by hand or with a calculator. Much more common to do it with a calculator. The upside is if I choose to do it by hand, the test statistic is going to have the same formula for all of these chi-square tests. It's the sum of the observed minus the expected squared divided the expected for every box in my table. For goodness of fit tests, where I'm looking at a single categorical variable, my degrees of freedom is the number of categories minus 1, not my sample size minus 1. That is important to keep in mind. That means that my k, my degrees of freedom, is going to be small, because I shouldn't be looking at situations where I have more than about 4 or 5 categories. Once we finished the do step, we have our test statistic and our p-value, we come to the conclude. We make a statement regarding the null hypothesis, reject or not reject, based on whether my p-value is less than or greater than my alpha. And then I write a sentence addressing the alternative. We're going to review these steps here really quick, and then we're going to do some examples so you can see how it works. Oops. So if I want to find my test statistic and my p-value with technology, which is more common, on the TI-84 calculator, I'm going to put observed in list 1 and expected in list 2. We want to be consistent with that. And then I'm going to go stat, test, and go all the way down to option D where it says chi-squared GOF. And it asks you for 3 pieces of information. Where is your observed? Where is your expected? What is your degrees of freedom? So list 1, list 2, categories -1. For GeoGebra, it's a little less complicated. For GeoGebra, you're going to make 2 lists ahead of time. List A is going to be your observed frequencies. List B is going to be your expected frequencies. And then you're going to call chi-squared test A, B. And GeoGebra recognizes that when you feed it 2 lists, this must be a goodness of fit test, and it'll calculate the degrees of freedom for you. When you draw this picture and you go to do the last step where you're marking the curve, you're marking where your p-value is, chi-squared tests are generally run as right tail. So your p-value is in the right tail, your test statistic is over here. Let's go ahead and do a few so you can see what this process looks like in practice. So first example says employers want to know which days of the week employees are absent in a 5-day work week. Most employers would like to believe that employees are absent equally during the week. Suppose a random sample of 60 managers were asked on which day of the week they had the highest number of employee absences. The results were distributed as shown. For the population of employees, do the days of the highest number of absences occur with equal frequencies during a 5-day work week? Test at a 5% significance level. So what they've given us here is they've given us some observed values based on input from 60 managers. So I should have 60 data values in this table, and if I add up really quick, 15 plus 12 is going to be 27, 36, 45, 60. So that does check out that we sampled 60 individuals. I want an expected as part of my state step. So I'm going to go ahead and add a row to my table, and I'm using the information that it says most employers would like to believe that employees are absent equally during the week, meaning I should see the same peak number of absences on each day. So to figure that out, we're going to take our sample size of 60 and divide it by the number of categories, which is 5. I have 5 days of the week. And I happen to know that 60 divided by 5 is 12. And we're going to go ahead and start with our state. So we're looking at days with the highest frequency or highest number of absences. And our null for this type of test is always that those occur with the same frequency. So I am my assumption is that the observed matches the expected. The alternative is that at least one category is different between the observed and the expected. So goodness of fit is asking, does this distribution match this distribution? The assumption is they match. The alternative is that they don't match. I also know back in the word problem we were asked to test at a 5% significance level. So I know alpha equals 0.05. Because I'm comparing an observed and an expected distribution for a single variable, days with highest number of absences, I know that this is a chi-squared GOF test. And my check is that all expected values are greater than or equal to 5. And mine are all 12, so we clear that condition. And my next step is to go ahead and calculate my p-value and my test statistic. So observed into list 1, expected into list 2, and then I'm going to call chi-squared GOF test. So stat tests all the way down to option D, and it asks me where my data is. So let's go put our data in a calculator. Observed in list 1, expected in list 2. And then my degrees of freedom, in this case, I have 5 categories. K equals 5. So my degrees of freedom should be 5 minus 1, which is 4. And then let's see what our calculator spits out. So it gives us a test statistic of 3. And it gives us a p-value of 0.5578. And I'm going to go ahead and draw my distribution. And I know that the mean of the distribution should be at the degrees of freedom, which is 4. And in this case, I know my test statistic is at 3. So my test statistic is closer to the peak than the mean is, meaning that represents a decent chunk of the curve, and that's why I'm getting more than half of the curve as my p-value. Since our p-value is much greater than our alpha, we're going to reject the null. Or fail, sorry. I'm sick and my brain is fuzzy. We are going to fail to reject the null. Reject the null when p-value is low. P-value is large, we're going to fail to reject. So my summary would be, because my p-value is greater than my level of significance, we fail to reject the null hypothesis. We do not have convincing evidence that the distribution for the highest number of absences is different from an equally distributed distribution. Let's go ahead and try 2 more. Make sure we have a feel for it. So the next one says, a geneticist is studying the gene pattern of eye colors in a group of white mice. He observed a random sample of mice from the lab and found that 110 had red eyes, 57 had brown eyes, 32 had pink eyes, and 13 had blue. His model suggests that the distribution of eye color should occur in a 9:3 to 3:1 ratio. Is there evidence that the geneticist model is not accurate? Use a 5% significance level. So I'm looking at the eye color of mice. Specifically of white mice. And I want to look at their distribution. So I'm going to have observed and expected, and I'm going to list the eye colors in the order they were mentioned. So red was first, followed by brown, pink, and then blue. And first I'm going to go ahead and list what we were given. So in the sample, we had 110 mice with red, 57 with brown, 32 with pink, and 13 with blue. Expected said we expect those to occur red to brown to pink to blue at a ratio of 9:3 to 3:1. And 9 plus 3 plus 3 plus 1 is 9 plus 6 is 15 plus 1 is 16. So I know the proportion for each of those categories. I expect that red would be 9/16, brown and pink should be 3/16, and blue should be 1/16. I'm going to take that and multiply it by my sample size. To figure out sample size, I need to add up the total number of mice I observed. So 110 plus 57 plus 32 plus 13, we have 212 mice total. So I'm going to multiply that sample size, n equals 212, by each of those proportions. So 212 times 9 divided by 16, and I get 119.25. And then 212 times 3 divided by 16, I get 39.75. And then the last one, 212 times 1 divided by 16, and I get 13.25. Comparing the observed to the expected, I know that last category is really close. This one's kind of close. This one's a little bit more off. This one's a little bit off. None of them are horribly off. And the question is, based on this sample data, do I have reason to suspect that this does not match what I'm actually seeing in reality? So we'll go ahead and set up our null and our alternative. So null is the population matches the geneticist model. Not mole model, try that again. And my alternative is that the population does not match that model, meaning at least one category is different. We were given a level of significance of 5%, so alpha is 0.05. I'm comparing a single categorical variable and a single sample to an expected or predicted model, so I know that that is a chi-squared GOF. And I know that all of the expected are greater than or equal to 5 because my smallest is 13.25, so we meet the conditions for that. we'll go ahead and use chi-squared GOF test on our calculator to find our test statistic and our p-value. So observed into list 1, expected into list 2, and then degrees of freedom, I have 4 eye colors, so my degrees of freedom will be 3. So let's go ahead and get that in our calculator real quick. And then stat tests chi-squared GOF. Change the degrees of freedom for this test to be 3. And we get a chi-squared of 9.7 with a p-value of 0.0211. So our p-value of 0.02 is less than our alpha of 0.05. And when p-value is low, reject HO. So we are going to reject the null hypothesis. Because our p-value is less than our alpha of 0.05, we reject the null. Therefore, we have sufficient evidence to support the claim that the geneticist model is not accurate. Alright, if you have any questions on the examples that you saw, feel free to send me an email or drop by office hours. Otherwise, I'll see you in our next video.